So let's continue talking about thermal properties and heat, internal energy, and thermal concepts in topic 3.2. And we'll start by talking about heat capacity. And I know right about now you're probably starting to get excited because this is reminiscent of chemistry. And you remember how excited you were when you got to do all of those math problems that were related to thermal energy and specific heat capacity and heat capacity in general. And so, yes, we do get to do more of those in physics. And let's start just by talking about the heat capacity, which is slightly different from the specific heat capacity. The heat capacity is the amount of energy that it takes to raise the substance's temperature by some degree Kelvin. And so when we're talking about the heat capacity, or the thermal capacity as it's sometimes called, we're talking about the amount of energy for an entire substance. And so if we think back to our example that we used in the last set of notes with the two separate sets of water. We have the bathtub full of water and we have the cup of water. They have the same average kinetic energy because they're at the same temperature, but they have different amounts of total energy. Well, that's where the distinction between specific heat and just heat capacity come in. The heat capacity of the bathtub full of water is much, much greater than the heat capacity of the cup of water because it takes much more energy to raise the temperature of the bathtub of water than it does to raise the temperature of the cup of water because there's so much more. And so there is our distinction between just heat capacity or thermal capacity and specific heat capacity. The heat capacity is the total body, the total amount of the substance, whereas the specific heat capacity is per unit mass, and we'll talk about that in a second. But when we're talking about heat capacity, if a specific substance has a very high heat capacity, so a high energy per degree Kelvin, that means that it's going to take a lot more energy to raise the temperature of that substance than if it had a low heat capacity. And the opposite is also true. If something has a high heat capacity, not only will it take more energy and more time, relatively speaking, to increase the temperature, but it also takes more to decrease the temperature because it has to get rid of more energy than something with a lower heat capacity. And the units there are going to be joules per Kelvin, energy per degree temperature or per degree Kelvin. Then we have our specific heat capacity, and the specific heat capacity is how much energy it takes to raise 1 kilogram of an object 1 degree Kelvin. And so there again, as we mentioned, the big difference, the thermal capacity or heat capacity is how much it takes to raise an entire substance per degree Kelvin. The specific heat capacity is how much it takes to raise 1 kilogram of that substance 1 degree Kelvin. So our bathtub and our cup of water, if this is our bathtub that's full of water, it has a whole lot of water, and then we have our glass of water, which is significantly less. So let's change that to blue. So the heat capacity of the bathtub is much, much larger than the heat capacity of the cup, but the specific heat, which is our lowercase c, and again this is capital C, and we'll say BT for bathtub and little c for cup. The specific heat, so the amount that it takes to raise 1 kilogram 1 degree Kelvin, is the same because they're both water, and so it takes the same amount of energy. One kilogram of this water is the same as 1 kilogram of that water. So the heat capacity of the bathtub is much larger, but the specific heat capacity of each is the exact same. And so our equation for specific heat capacity is the change in energy divided by the mass times the change in temperature, which then gives us units of joules per kilogram Kelvin. If we think about those units, it's the energy per kilogram per degree Kelvin. And when we're solving problems with this, when we're doing labs with this, remember that 1 degree Kelvin and 1 degree Celsius are the exact same amount, and they have the degrees are equivalent. So if something has a change in temperature of 10 Kelvin, then it's going to have a change in temperature of 10 Celsius degrees also. And so it's not required, or you don't have to convert to Kelvin when we're working with temperatures if we're just talking about the change in temperature. Now, specific heat capacity is a property of a substance, and so all substances have their own unique specific heats. Something like aluminum has a low specific heat. Something like water has a very, very high specific heat. And there are a couple of reasons for this, but the biggest one is that what we're really looking at is the amount of energy it takes to raise 1 mole of any substance. And there are a couple of reasons, but the main one is that they have different molar masses. If we were going to look at the amount of energy that it took to raise 1 mole of any substance by 1 degree Kelvin, those values would be all about the same. But because we're looking at the amount of energy per kilogram, now they're all going to be drastically different, because the number of molecules in 1 kilogram of a substance varies depending on the molar mass of the substance. And so something like lead has a very large molar mass, and so 1 kilogram of lead is going to have fewer molecules or fewer atoms than 1 kilogram of, say, aluminum. Aluminum is going to have more molecules. And remember that energy, when we're adding energy to the substance, it's roughly being distributed evenly among the molecules. So if we have 1 kilogram of a substance, the more molecules there are, the more that energy is going to get spread around. And so the average kinetic energy of each molecule is going to increase roughly the same amount.